So we have this relation. Let's say we want to know what dy dx is. In other words, with shorthand notation, we want to know what y prime is. Sorry about the writing there. We want to take a derivative with respect to y. Now this one, right now it's not arranged so that it's an explicit formula for what y is. In other words, it doesn't say y equals something in terms of x. But we could do that. Subtract 4x from both sides, and then divide everything by 2. Now we have an explicit formula for y in terms of x. Y is 4 subtracted by 2 times whatever x is. And when we take a derivative, this one's nice and straightforward. It's just the power rule. Derivative of 4 is 0. The derivative of negative 2x is negative 2. Okay? So this relation's more complicated though. Right? This one we could get y by itself. Try to get y by itself here. Actually, you can. Let me just change. I'll come back to it in just a second and do that problem. Before, you could get y by itself, so that's why I wanted to avoid that. So let's say it's x minus xy squared plus y. Try to get y by itself. Subtract that x that's hanging out by itself from both sides. Now what do we do? Sometimes there's some algebra tricks we can use regarding knowledge of quadratics where we could factor by completing the square. Maybe you can eventually get y by itself. But if we're looking for dy dx, we could do that quicker using implicit differentiation. And with implicit differentiation, we're saying, here, we'll go back to this original problem. We're saying, look, we don't know what y is in terms of x. We can't get this by itself. But we can at least write the derivative notation for what the derivative of y is, right? So here, if I try to take a derivative with respect to x, the derivative of x, that one doesn't need anything special. That's just the power rule. But this term is special because y is some sort of function of x that we haven't clearly defined yet. When I take a derivative of this term, I have two different functions of x that are multiplying to each other. The derivative of x is 1 times y kept the same. The second function kept the same. Plus the first function kept the same times the derivative of the second function. Now the derivative of y with respect to x, this time we don't have a clear formula like we did in this problem up above. But instead, what we can do, we can write y prime because that's the symbol for the derivative of y, right? And that's the implicit differentiation step. Okay. Just remember, sometimes like if you're trying to take a derivative with respect to x of y squared, you got to use the chain rule, right? There's a power function going on. The 2 is on top of y, so the 2 comes down and multiplies. And then you take a derivative of the innermost function. So the derivative of y squared with respect to x is 2y prime. Okay, so that's just an aside. That's not this problem. But and so again, when we're taking derivative of y with respect to x of y, that's going to be y prime. We don't know what it is in terms of x. So we're just going to symbolize the derivative with y prime. And the derivative of 10 is just 0. There's our derivative. I mean, the last step you want to do is just get y prime by itself algebraically. So we can distribute that minus sign. Okay, and then the goal is to get y prime by itself, so we don't want these terms on the left side, so let's subtract 1 from both sides. We don't want this term over here because we're trying to solve for dy dx. We're trying to get y prime by itself. So we'll add that y to both sides. That's a prime down there. And then look, I have a y prime and a y prime. Let's factor out a y prime. And then we're trying to get y prime by itself. So we'll divide both sides by negative x plus 1. Because that makes this term cancel out and gets y prime by itself. So here, we're done now. This is the derivative of y. And then if you wanted to go further, you could put this one in terms of x because you... Oh, wait. No, never mind. Okay, so there's our derivative of y with respect to x.